everyone. So this set of notes technically covers two lessons, lessons 2.4 and 2.5. All of that's related to exponential functions and exponential modeling. This first video I'm going to cover just part of the notes, and then I'll do a second video to kind of cover the second half. So let's review what we remember about exponential functions. The most basic thing you need to know about an exponential function is that it's formed by repeated multiplication. That's essentially what an exponent is, right? Is multiplication over and over again. So any type of real life situation that involves multiplying by something repeatedly, so if you're doubling or tripling or something like that, or a lot of percentage problems, those are all going to form exponential functions. So this is the general form of an exponential function. This should look familiar to you. You saw this last year. And when we're looking at this form, these letters have some significance. So the A is always your initial value. The B is called your growth factor, and I'm putting growth in quotation marks here because you can also have exponential decay, but we still refer to this as a growth factor even if it's not technically growing. And then the X represents, typically it's like a measure of time, but it's how many times you're multiplying. Because if you think about mathematically what's happening here, you're starting with some value and then multiplying by this growth factor over and over and over again, okay? Just a quick reminder here how to work with percentages. If you have a growth factor that is a percentage, and that could be a growth or a decay factor, if it is true growth, you have to remember to add it to 100%. So for example, if I say to you in a particular problem that we have 9% growth, you have to think of that as 109%. You have to think of that as you're keeping 100% of what you currently have and adding 9% on. And so then in the actual equation, you would use a B value of, and I didn't leave myself enough room here, but 1.09. Okay, so having that 1 in front is really, really essential to be able to grow. Because if you just multiply by 0.09, you're not going to grow at all. You're going to shrink. Okay. If it's decay, we have to remember to subtract from 100%. And I'm probably going to give myself even less room this time. So if I have 9% decay, I have to think about what percentage am I keeping. So if I'm losing 9%, that means that I'm keeping 91%, and I would make my B value 0.91. So you have to remember to deal with this 100% when you're dealing with percentages, because if you just multiply by the percent by itself, you're not going to get the correct value for that next step, let alone all of the ones after that. Okay? So again, you should have learned that last year, but just to remind yourself, that's how those growth factors should work. Okay, so example 1 here is really similar to the types of problems you were doing last year in Algebra 1. 1995, the U.S. population was estimated at blah, 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 predicted to grow at 0.9% per year. So just kind of labeling the pieces that we have here. The current population, or if we're considering current to be 1995, that's our A value. And then this is what's going to give me my B value. But what I have to remember is that if I'm growing at this percentage, I'm going to do 100% plus 0.9%, which gives me 100.9%. And that means in my problem, I'm going to be putting in 1.009. If you struggle with how to move those decimal places, there is no shame in typing this into your calculator so that you can see this number in front of you. I realize this math should be easy, right? But sometimes it's helpful to see this number in front of you and then physically move the decimal point over twice. Okay, so once we have our A and our B, really we're set to go here. We can say y equals my A value. Now here's what I think I'm going to do. I think I'm just going to put 264 in as my A value instead of dealing with all those zeros. This is 264 million people. Okay, so I am just going to know that my answer is going to come out in millions. So if I start with a value of 264, whatever answer comes out of my equation, it'll be that many million people. Here's my B value that we just figured out was 1.009. And then I'm going to the power of X, where X represents years after 1995. So if I'm trying to estimate the population in 2010, which is what this next question is asking, I have to think about what my X value should be. How many years after 1995 is that? That would be 15. So I'm going to do this calculation. And again, I cut those zeros off of there just to make it easier on us when we go to type it in our calculator. It'll also make it so our calculator isn't going to have an issue with overload or anything like that. Okay. So I'm going to go 264, 1.009 to the power of 15. Okay, and let's see, it's an estimate, so I would probably feel safe rounding this to 302, okay, rounding to a whole number here. So maybe I'll change my symbol here to show that I'm estimating here, but I would say 302 million people is what I would predict in the year 2010. Now, just be careful. If you pull a trick like this where you use the 264 instead, you do have to make sure to indicate either in numbers or in words that this is a million value, right? If you had just left your answer as 302, that would be an issue. Okay, couple of reminders of exponential graphs, what the graphs look like. And then we're going to talk about some properties of these graphs. So when I'm looking at an exponential function, they always have kind of this swoop to them. So this would be an exponential growth function. Okay. If I were to do decay is going to look very similar, except it's going to start high and then go low. It's going to go like this. Okay. So that's what exponential functions look like. They start slow, and then you'll notice that they always grow very quickly. That's just how exponential growth kind of operates. Is if you're doubling or tripling or even growing by a percentage, it's going to start off pretty slow here at the beginning, and then it's going to grow very, very quickly. These always end up growing faster than a linear function. We're going to kind of explore that concept in the next lesson. Couple of things you need to know about the graph here is that this y-intercept is always at that initial value. It's always at the A value. And we're going to write this down more formally on the next page, but just to remind you, notice that these graphs never come down and cross the x-axis. And that's because when you're working with multiplication, you can never take a number that's positive and somehow turn it negative, okay? If your B value is always greater than 0, which we probably should have written that down up here. I apologize. When you're working with these exponential functions, we never work with negative B values. If we want to make this thing shrink, we subtract from 100%. So something smaller than 1 is going to lead to decay. So we should probably indicate here, I'm going to use a different color, that A always has to be greater than 0 and B always has to be greater than 0. Okay, our A value and B value are always greater than 0. Should also probably note that when B is greater than 1, that's when we're going to have growth. When B is less than 1, that's when we're going to have decay. Because if you think about multiplying by something that's less than 1, that's always going to give you a smaller value. But if we also take this into consideration, we have to say smaller than 1, but also greater than 0. Okay? So when B is larger than 1, something like this, or 2 or 3 or whatever it happens to be, that's always going to lead to growth. That's always going to lead to one of these situations here on the left. Sorry, you can't see my picture. If you have a B value that's between 0 and 1, and when we say between 0 and 1, really we're talking about like decimals and fractions. But if I have a B value that's between 0 and 1, that's when I'm going to be in a decay situation. Regardless, either way, you always have this line on the graph, the x-axis, that the graph never touches and never crosses. And like I said, that has to do with the fact that you can never flip from positive to negative using these values. Okay, that line is called an asymptote. And I do know we talked about this last year. And for exponential functions, whether it's growth or decay, the asymptote is always that x-axis, otherwise known as y equals 0. Okay, so those are two things about the graph that you're going to need to know. We're going to write down a few more things on the next page. Okay, so on that next page, my next page, the next example, just real quick, I want to mention something. So I've got three graphs there, three functions, f of x, g of x, h of x. Just from looking at them, I can tell you that this is going to be growth and this is going to be decay based on that thing that we just talked about, that growth always has a b value that's larger than 1. Decay always has a b value that's smaller than 1. So again, right off the bat, I can say this is growth, this is decay. This one's kind of weird though, because it's got a negative x value. If we were doing a problem that had to do with time, a negative x value would mean that we're going like backwards in time. So this would be like growth, but going backwards, okay? Let's look at a picture of this one. And I think I have a window open and ready here for you. Oh, there it is. Okay, so here are my three functions. And like I said, I'm expecting that 6 to the power of x to be growth. That's what you're seeing there in red. Let me make that a little more obvious for you. This one I'm expecting to be decay, so the blue one there. And it's kind of hard to see, but if I were to zoom in real close, you would notice that that red line and blue line never actually cross the x-axis. The farther I zoom out, the harder it is to tell that. But so let's think about this one. If this is like growth in reverse, what are we expecting that graph to look like? And it's going to show up in green here. So take a look. Notice that that green graph is exactly the same as the blue graph, okay? Because like I said, growth in reverse is really going to be almost like decay. That's a weird way to think about it, but if you think about this from an algebraic point of view, a negative exponent always takes this thing down here and flips it to the reciprocal, right? So this 6 to the negative x is really the same thing as the reciprocal of 6 being raised to the power of x because of that negative exponent, okay? This is not a huge deal in the world of exponential functions, but it does come up in your homework, and wanted to make sure you understood that relationship, that a negative exponent is okay. Remember, your a and b values are never going to be negative, but a negative exponent is okay. It just kind of flips the direction that your graph is heading. So last thing I want to talk about, and let's see, I'm going to try to do this where we can still see the graphs that we just drew a second ago. So there's our graphs. Here's our questions that we're answering. We want to talk about some of these properties, okay? And a lot of these properties don't change even if I switch the numbers that are in my function. So if I look at both of these graphs, and it doesn't matter what a is or b is, what's the domain of my function? Well, domain is asking you what x values are allowed. And if you look from left to right, this graph spreads out forever. It goes forever to the left, forever to the right. So your domain of exponential function is always all real numbers. The range is asking you what y values do you cover. And notice we talked about that asymptote. There's this line here that this graph will never cross. It always stays above the x-axis, which is the same thing as saying all reals greater than 0. Notice I'm not using an equal bar there because it never actually touches 0. Okay, it always stays above 0. You could also say all real positive numbers, which would look something like this if I were writing it in symbols. Okay. The y-intercept we kind of talked about. The y-intercept is always going to be at whatever the a value is. So as a coordinate, that would be 0, a. We also talked about the asymptote. The asymptote is this magic line here that this graph never crosses. It's going to get closer and closer and closer, but it's never actually going to touch it. Okay. And so the easiest way to think about that is thinking about this decay graph. Let's say that I'm taking something and cutting it in half. Maybe I'm taking a sheet of paper and I'm ripping it in half forever, okay? So I rip it in half, and then I rip it in half again, then I rip it in half again, rip it in half again. Am I ever going to get to a point where I have no paper left in my hand? I mean, I might get down to like the molecular level, but if I'm only cutting in half, I'm always going to be left with half remaining, right? And that's why this can never actually equal 0, because it will never actually touch that x-axis. So my asymptote is always at y equals 0, otherwise known as the x-axis. And then end behavior, just real quick. I want you to know that when your growth factor is greater than 1, so when we're talking about an actual growth graph, as you go to the right, as x approaches infinity, which is our way of saying as we go to the right, my y values are increasing forever, right? So y is also approaching infinity. This right here is just a fancy way of saying as I go to the right, my graph is going up and up and up forever. But when I'm dealing with a growth factor that's less than 1, so when I'm dealing with decay, what's going to happen as I go to the right, my graph is coming closer and closer and closer to the x-axis. So I would say as I go to the right, my y value is actually approaching 0. That's what all of this is saying in symbols. Okay? I will tell you that this, and this question are going to come up a ton in your homework, on your quizzes, and they're going to throw you all different equations with all different values in there for A and B. Those answers are never going to change. If it's an exponential function, this is your domain, this is your range, this is your asymptote, every single time, okay? And I mean, these things are always going to stay the same as well, but I know these three are the questions that I get asked the most often. Okay, I'm going to stop here and I will pick up in the next video with exponential modeling, and we'll talk how to do some of that in your calculator and how that relates to some of the stuff we just talked about. So hopefully that was helpful to get you started on 2-4.